Hi, my name is Divya, and today I'm here to talk about our work on learning to limit data collection via scaling laws, in which we offer a computational interpretation of the legal principle of data minimization. This work is joint with all the people on the slide. From left to right, it's me, Samira, Fernando, Michele, and Aja. The reigning attitude towards data sets is the bigger, the better. And this has meant that data collection in machine learning is often unrestricted, where companies aggressively collect personal data in pursuit of profits. This neglects the real and tangible concerns of data overcollection, including privacy, liability, and storage. So let's say we're building a birth control pill recommendation system. What a company might do is collect every feature, all of it from each of its examples or users, and store this information forever in the hopes that it might be useful to some predictive task they think of in the future. This is obviously problematic because these features are sensitive and often concern things like user pregnancies or menstrual cycle symptoms. And even in recent months, we've seen the dangers of sharing that type of data with companies who can then sell it to others. What the GDPR imagines and also requires is that companies collect relevant features, an adequate number of examples, and that data collection and storage must be limited. Each of these ideas is encoded in the legal principle of data minimization, which is a part of the GDPR. Despite the fact that it was instantiated in 2016, it's faced little adoption due to a lack of technical guidelines and computational interpretations. This leads us to the central question in this work: how do we formalize limited data collection? Our answer is a framework that we call FIDO, which stands for a framework for inhibiting data overcollection. And the key idea here is that we learn a model's performance curve as data is collected to enforce a stopping criteria. So it happens in 3 steps. The first is to collect data. The second is to fit a performance curve using the collected data. And the final step is to evaluate a stopping criteria based on the estimated performance curve. To talk a little bit more about the second step of fitting the performance curve, we do this by using the acquired data A and a pre-specified performance metric sigma. And what we do is subsample the acquired data to different sizes, evaluate the performance of a trained model on each subsample on a validation set V, and then use these sample size performance pairs to fit a performance curve. In particular, we modeled a performance curve in a specific way in which we modeled different stages of the data collection process with individual power law curves. This is distinct from prior work, which typically models the whole performance curve with one power law. In the final step, we evaluate the stopping criteria. So this could be any data minimization objective defined using the performance curve. And in the main text of our paper, we use a returns-based criterion. So we use the estimated performance curve to cease data collection when the derivative of the performance curve falls below some threshold on the return given additional data. There's a lot in this paper. The task that we focus on is recommendation, and we look at multiple data sets, feature acquisition algorithms, performance curve families, and data minimization objectives, in addition to even more. So if this is something that's interesting to you, I recommend you check out the paper. I do want to share one result that I found particularly exciting, which is that common performance curve families systematically overestimate the return on additional data. So here what I've plotted is illustration of a diagram from a paper in 2017 on the stages of data collection that identifies these 3 stages: the small data region, the power law region, and the diminishing returns region. On the x-axis is the training data set size, and on the y-axis is generalization error, so lower is better. What happens when you fit a single power law curve is that you estimate the curve accurately in the power law region, but when you use that curve to extrapolate into the diminishing returns region, you overestimate the return or underestimate the error given additional data. We see that this behavior bears out in practice across multiple data sets and multiple performance curve families. As a brief summary of our other findings, we also find that modeling each stage of data collection separately produces a performance curve that's often as accurate as an oracle with access to the full data set. We also find that active feature acquisition algorithms lead to both noisier stopping criteria and can lead to data collection concentrated in a small number of users. And finally, we also see that user-specific performance curves, modeling the amount of data per user for that versus that user's specific performance, does not always improve with more data and requires alternate assumptions and alternate performance curve families to model accurately. In sum, our experiments reveal guidelines for design choices across the data minimization pipeline, in addition to future directions for operationalizing data minimization in machine learning systems. If you'd like to chat, you can visit our poster, email me, or talk to us in person. Thanks for listening.